Hard part is getting the space helmet on the Canary. Yes, that's always a challenge. All right, a little bit of hype. We see a little bit of hype there. There is mining the sky. Untold riches from asteroids, comets, and planets. Boy, oh boy, do we want some of that money. Mind stretching by Space News. And then over on the right, the colossal untapped value of asteroids. Estimated value of our most valuable asteroids in quintillion dollars. Now, I struggled with quadrillion. I think quintillion is got to be 10 to the 18th. So I have no idea where these numbers come from. I should also point out I don't know any of these asteroids. So anyway, so there is a one asteroid with 10,000 quadrillion dollars on it. So it's like, okay, yes, please, we'll take some of that. But perhaps because people are so, well, should I say ignorant about what asteroids really are, they can't critically assess these claims. Now, this is an 18-minute video.
Just a couple of years ago, it seemed that space mining was inevitable. Analysts, tech visionaries, and even renowned astrophysicist Neil deGrasse Tyson predicted that space mining was going to be big business.
The first trillionaire there will ever be is the person who exploits the natural resources on asteroids.
In a 2017 note to investors, a Goldman Sachs analyst wrote, "Space mining could be more realistic than perceived. A single asteroid the size of a football field could contain $25 billion to $50 billion worth of platinum." Space mining companies like Planetary Resources and Deep Space Industries, backed by the likes of Google's Larry Page and Eric Schmidt, cropped up to take advantage of the predicted payoff. After all, the holy grail of asteroids, known as 16 Psyche, had an estimated worth of 10,000 quadrillion dollars. But fast forward to 2022, and both Planetary Resources and Deep Space Industries have been acquired by companies that have nothing to do with space mining. And humanity has yet to commercially mine even a single asteroid. But that hasn't stopped a new crop of startups from trying.
Astro4's mission, obviously, is to leave Earth with a vehicle, go out to an asteroid, mine it for its rare earth elements, and then return that to Earth to be sold.
Transaster was founded with the mission of working towards the vision of harnessing the resources of space, especially the asteroids, for the betterment of humanity. There's enough material in the asteroids to support a population of 1 trillion people.
So far, the closest we've gotten to mining an asteroid has been prospecting missions. In October 2020, NASA collected a small dust sample from the asteroid Bennu as part of its OSIRIS-REx mission. The sample is not due to return until 2023, but during the mission, scientists were surprised to learn that Bennu's surface was not as solid as predicted. In December of 2020, Japan's Aerospace Exploration Agency brought back a sample of an asteroid known as Ryugu as part of its Hayabusa 2 mission. To collect the sample, the agency fired a projectile at the asteroid and scooped up the flying material. Like Bennu, scientists found that Ryugu also had a rubble pile surface. Although these recent advancements by the likes of NASA and JAXA have provided useful information on the composition of asteroids, space mining has yet to become a commercial endeavor. So what's taking so long? For one, space mining is a long-term endeavor, and one that VCs did not necessarily have the patience to support.
If we had to develop a full-scale asteroid mining vehicle today, we would need a few $100 million to do that using commercial processes. It would be difficult to convince the investment community that that's the right thing to do.
Take NASA's OSIRIS-REx mission, for example, which is expected to take 7 years to complete and cost over $1 billion, all to bring back a handful of asteroid material. And Planetary Resources? Despite its millions in investment, the closest the company ever got to asteroid mining was launching a satellite to prospect future targets. In fact, the mining of celestial objects has become a point of satire, showcasing corporate greed, as seen in this clip from Netflix's 2021 film, Don't Look Up.
This comet hurtling towards us from deep space actually contains at least $32 trillion of these critical materials, critical to technology.
I'm sorry, is that why you aborted this entire mission? Is because you're trying to mine the comet for rare minerals? I think we should hold off.
Others say mining precious metals to sell on Earth never made much economic sense.
If you look at platinum, the production cost, platinum is around $1,100, even more, and the price per ounce platinum is less than $1,000. So it means the earth mining is not profitable right now. When analysts made their predictions, they were looking at the amount of the precious metals and materials in the asteroids, and they didn't look at the economies of the industries.
In today's economics, and in the economics of the near future, the next few years, it makes no sense to go after precious metals and asteroids. And the reason is the cost of getting to and from the asteroids is so high that it vastly outstrips the value of anything that you'd harness from the asteroids.
When we think of space mining, precious metals likely come to mind. But in fact, asteroids can contain other materials, which, in the short term, could be even more viable.
There is mining materials in space for use in space. And then there is return to Earth. The return to Earth ideas, they have to compete against terrestrial markets for those same materials. That would be very challenging, and it may happen someday, but it's most likely in the far future. But in the near term is mining materials for use in space. The number one item is water. There are certain types of asteroids that have hydrated minerals. We can process those minerals to release the water. Our best use of the water is actually as processing to make it into a rocket propellant. And then with rocket propellant, we can move around space more readily. We don't have to launch all of our propellant from Earth.
Gabor Sechi agrees that when it comes to mining the cosmos, we should look beyond precious metals.
In short term, we should focus on helium and water. Helium because it's not readily available on Earth, and water because it has a potential use in space.
An attorney by trade, Sechi spent several years working with the European Space Agency and decided to focus his legal expertise on advising space startups. He's now an advisor for an Australian startup that aims to mine water and helium-3 from the moon. An isotope of helium, helium-3 has applications in national security, medicine, and cryogenics. Recent helium shortages have forced some research labs to suspend their projects and induced national security concerns. Knowing what we can mine is one thing, but figuring out how to mine it is another. Braced with new data from NASA and JAXA, scientists and companies have had to devise new ways to mine asteroids.
In older thinking, landing on asteroids and anchoring to them and drilling or excavating were the scheme. That may now look less viable because of what we've learned of asteroids.
Scientists typically categorize asteroids by their composition type. C-type or carbonaceous asteroids are most common and are made up of clay and silicate rocks and contain water. S-type or stony asteroids are the second most common and are generally made up of a metallic nickel-iron and magnesium-silicate mixture. Finally, M-type or metallic asteroids account for the rest of the known asteroids and are thought to be primarily made of nickel-iron.
What we've learned is that most asteroids are rubble piles as opposed to one big mountain-sized solid piece of material.
Based on this new understanding of asteroids, TransAstra has been working with Dreyer to develop a technology it calls optical mining.
The optical mining process that we've invented involves step one, capturing the asteroid in an enclosure, what we call a capture bag. The asteroids are typically spinning, because that's what they do in space. Our spacecraft matches the spin with the asteroid, flies the bag over the asteroid, captures it, and cinches it down tight so we have positive control. Now, once we contain the asteroid in our capture bag, then our solar reflectors redirect that concentrated sunlight into the capture bag, and we use it to drill holes in the asteroid and heat up the material and drive the volatiles, the water and the other gases, out of the minerals. And then we can capture those volatiles in an ice trap.
TransAstra is initially focusing on mining water to make rocket propellant, which Sersos says will enable low-cost space travel. But eventually, the company plans to harvest everything on the periodic table.
We've calculated that a single TransAstra mining vehicle, one we call the Honeybee, can fly out to an asteroid and bring back about 100 tons of water and other ices in a single mission. It's worth about $1 billion. And we know that because we have a contract to deliver 100 tons of ice in geostationary orbit from a publicly traded company.
But that kind of revenue is still a ways off. TransAstra is funded by about $5 million in grants and contracts from NASA and several million in venture funds. To keep itself above board, Sercel says that TransAstra is focusing on developing its intellectual property piecemeal, using the tech that will eventually be incorporated into its mining missions to satisfy already existing market needs.
One of the commercial opportunities is traffic management. With our Sutter telescope technology, we can turn a small, inexpensive commercial telescope into a powerful instrument that can see space traffic and orbital debris, something the size of a toaster oven, all the way out to the orbit of the moon.
TransAstra has already deployed its telescope system at 2 observatories in the US, with the technology currently being used for asteroid prospecting. Eventually, TransAstra also plans to launch its telescope tech into space to be able to see deeper into the universe.
Likewise, there's a burgeoning orbital logistics business today for delivering satellites to their orbital destinations from where rockets leave them off.
To do this, TransAstra is developing an orbit transfer vehicle known as Worker Bee, the body of which can also be used for its asteroid mining vehicle. But the company has yet to operate any of its technology in space. Still, Sercel says that TransAstra is already making a small amount of revenue from starter contracts for its satellite tugging services and has brought in more than $500,000 from its Sutter telescope tech in the form of NASA R&D grants.
Our plan is to be revenue positive at every step along the way while we're building the company and using these near-term businesses to mature the technology. And then as you do that, you have all the pieces in place to go out and start asteroid mining.
Our mining process is 3 stages. We have to do a vaporization of the material. So we're going to take an asteroid and essentially vaporize it into a cloud of atoms. And then we're going to ionize it. So we're going to each take that cloud and positively charge all the atoms. And then once we have a whole bunch of positively charged atoms, we can sort them.
Astroforge is another early-stage company trying to make space mining a reality. Founded in 2022 by a former SpaceX engineer and a former Virgin Galactic engineer, Astroforge still believes there's money to be made in mining asteroids for precious metals.
We have a limited amount of rare earth elements, specifically the platinum group metals. These are industrial metals that are used in everyday things, your cell phone, cancer drugs, catalytic converters, and we're running out of them. And the only way to access more of these is to go off-world.
Astroforge plans to mine and refine these materials in space and bring them back to Earth to sell.
The key technology that we're developing is our ore processing system. So that system consists of the excavation subsystem that moves the material from the asteroid into the spacecraft. And then there's that refinery piece that extracts the valuable material and removes all the unnecessary material that we can't actually sell on Earth.
To keep costs down, Astroforge will attach its refining payload to off-the-shelf satellites and launch those satellites on SpaceX rockets.
There's quite a few companies that make what is referred to as a satellite bus. This is what you would typically think of as a satellite, the kind of box with solar panels on it, a propulsion system being connected to it. So for us, we didn't want to reinvent the wheel there. The previous people before us, Planetary Resources and DSI, and they had to buy entire vehicles, they had to build much, much larger and much more expensive satellites, which required a huge injection of capital. And I think that was the ultimate downfall of both of those companies.
SpaceX really allowed a lot of companies to start in the aerospace world, basically because of the lowered cost to access space. So now we can kind of leverage that and really focus on just the technology piece.
Astroforge says it's raised $23 million in venture capital funding and plans to conduct several test missions before launching its first official mining mission in 2025. The company is targeting near-Earth asteroids, with a single mission expected to take around 2 years.
Our first mission is to send up a refinery. So we are going to take an artificial asteroid. We are exactly concentrations we've created, so we are going to show that we can extract platinum from this in zero-G in a vacuum. Mission number 2 for us is a prospecting mission. This is where we go out to an asteroid, we make sure we can get to an asteroid, our spacecraft can last for 2 years, and we can take high-resolution images of it to make sure the surface is what we expect it to be. The third mission, we now introduce our extraction arm to that mission. We're going to go out, we're going to take a sample of the asteroid, bring that back to Earth, and and we'll study it on Earth to understand exactly what the concentrations are of that asteroid. Our fourth mission is where we put all those pieces together. We send out our mission with the excavation arm, we put our processing facility on it, and we repeat those steps in order to get platinum.
Like planetary resources and deep space industries before them, today's asteroid mining companies face a large number of challenges. The first is uncertainty stemming from the lack of an established international law to govern space mining. At the moment, most space activities are governed by the Outer Space Treaty, which was established during the Cold War. One of the treaty's principles prohibits the appropriation by individual nations of any celestial bodies, such as the moon or asteroids, and requires that any space exploration and use should benefit the whole of humanity.
When it comes to space mining, the whole discussion is about whether Outer Space Treaty allows or bans space mining. One of the interpretations what we should do with the mined minerals is to share the benefit which is coming of it, and it's not clear whether the benefit should be the wealth which is emerging from mining of the space mineral, or whether mining can provide us with some scientific knowledge, and the benefit would be just sharing the scientific knowledge.
In the absence of an established international law governing space mining, some countries have taken it upon themselves to establish their own. The Commercial Space Launch Competitiveness Act, passed by the Obama administration in 2015, raised eyebrows when it gave property rights to companies for the materials that they mine from asteroids, though it stops short of granting companies ownership of the asteroids themselves. In the time since, Luxembourg, Japan, and the United Arab Emirates have established their own space mining laws. But Schmidt says not having an international law for space mining could be enough to dissuade some companies from trying to mine the cosmos.
I think that the national laws are not enough for the companies to overcome the legal uncertainty they observe, especially when you ask about the ownership. If they invest money and go to space and mine something, and the discussion about the ownership is not clear, they don't have certainty that what they are going to mine will be theirs, and they will have full freedom to use the material for whatever they want.
But Sercel says there's already precedent for this.
There's limited slots in geostationary orbit where you can put satellites. Once you have the allocated slot and the satellite, other countries and other companies are not allowed to go there and mess with it. So we're certain that when we go to an asteroid, capture it in a bag, and mine the resources from it, that we will own those resources.
Another challenge is even more basic: deciding which asteroids to target for mining in the first place. Prior to conducting their own missions, all early-stage mining companies have to go on is existing observation data from researchers, and a hope that the asteroids they have selected contain the minerals they seek.
The most challenging aspect of asteroid mining is really the asteroid itself. We have a lot of evidence and observations and scientific data, but we don't actually have a lot of truth knowledge, meaning there's only been a handful of missions that have actually gone to the asteroid. So you can design a perfect system, you can control all of these things, the technology piece you can control, the operations piece you can control, but you can't control what the asteroid is until you get there.
If the companies do somehow manage to extract the materials they're seeking, the next hurdle is selling them. Theoretically, an influx of precious metals introduced to the commodity market on Earth could be enough to crash it. But Astroforge says this is unlikely.
When you look at the supply and demand curve for platinum group metals, right, the total market cap of these metals is measured right around $60 billion. We're talking about bringing back $80 million per mission. So for us, it would take quite a bit of missions to really greatly affect the supply and demand curve as we go forward.
For now, commercial space mining remains highly speculative, with companies just starting to test out their tech and business plans. Still, experts believe that some form of asteroid mining will eventually take place. The question is when?
I think we will be able to mine an asteroid within the next decade. At the very least, this will be done as a proof of concept for a mining process, but possibly also include an actual sale of most likely water to be then processed into propellant.
In terms of the timeline for mining asteroids, for us, the biggest issue is funding. So it depends on how fast we can scale the business into these other ventures and then get practical engineering experience operating systems that have all the components of an asteroid mining system. But we could be launching an asteroid mission in the 5 to 7 year time frame.
If we have a developed and working space manufacturing industry, then I can imagine asteroid mining will become a valuable option, but it's not a 10 years time period. I believe that we are going to mine in space, maybe 20, 25 years from now.
All right, so number one thing about asteroids is they don't have a mineral system. So we've talked explicitly about mineral systems, and and they're implicit behind everything that we've gone over in all of the Muller chapters, is even if they don't identify it explicitly, it's clear, right? With the exogenic deposits like banded iron formations or uranium roll front deposits, you know that you can sort of understand the role of the different components in creating that deposit. Likewise for the endogenic ones, like porphyry coppers and the layered mafic, ultramafic intrusions. So, here we see one we saw earlier, where crustal different. So we got time, because after all, Earth is an active body. It's constantly reprocessing itself. And then on the scale, the globe to the craton to the province to the district to the deposit scale. And in this, you can see, okay, crustal differentiation, was a first step in making the ore deposits possible. And then there were geodynamic and tectonic processes that further processed it. And then the fluids get involved and start doing another concentration. And eventually, if conditions are right, we get a deposit. Now that takes time. And Earth has had, 4.6 billion years to do these kinds of things. And there are deposits of all different ages. So you could say, well, there wasn't 4.6 billion years for the Canadian Shield. There was only 2 billion years. Well, 2 billion years is still a lot of time. So the point is that because asteroids, for the most part, are, capture something that happened at the beginning of the solar system and since have done very little, with a few exceptions, and we'll talk about them, they don't have mineral systems in the sense that we expect them. So, but still there is value, and we're going to talk about the two kinds of value. There's two ways that we can use materials from asteroids. One is for use in space, right? In situ research utilization, and a lot of that, you could see how that might be useful on a place like Mars too, which is not an asteroid, but nevertheless, your in situ resource utilization that's what's going to happen, isn't it? We don't want to have to bring everything from Earth. And then there is, for return to Earth, certain high value materials, and we'll go over both of these. So for use in space, the ISRU, spacecraft fuel, construction materials, life support, so water, perhaps from ice and asteroids, but it could also be, there's ice on the moon and Mars. And these ices, water ice, can be split into hydrogen and oxygen for rocket propellants, oxygen for breathable air, water for drinking, washing, hydroponic agriculture. And then there are other ices as well. And, they also have uses. Oxygen, obviously, we've got it in there twice. Metals for construction, iron, nickel, cobalt, which are quite abundant in metallic asteroids, can be useful for structural materials in space. Aluminum, titanium, they're especially abundant in the lunar regolith, and also can be obtained from asteroids for lightweight structural materials. And then silicon for solar panels and electronics. These are things that could be used in space. For return to Earth, the high value materials. Now, I've got rare earths in there, and I meant to take that out, because there are really, rare earths are not an important thing in meteorites. So let's take that out. But preeminent among the high value elements are the platinum group elements. You know, we talked about platinum, palladium, rhodium, iridium, osmium, ruthenium. They're used in catalysts, electronics, green energy tech, and most metallic asteroids have concentrations far above Earth ores, and we'll talk about that. And then, of course, gold, which follows the platinum group elements in many cases, not always. And then there's helium-3, which is a rare isotope that's found in the lunar regolith. It could also be found in asteroids, and it's been proposed as something useful for future fusion energy, but it's still experimental. So those are the things that are more likely to be economically advantageous to return, to extract in space and return to Earth. So how do we figure out how to start asteroid mining? Well, it's pretty simple, you know. Figure out which asteroids to target, you know, go there and mine them, and then sell the product, whether it's in space or whether it's bringing them back to Earth. So, which asteroids should we mine? So, number one, where are asteroids found? So, I think everybody knows about the asteroid belt, which is between Mars and Jupiter. That's going to be hard to reach. That's going to be more expensive to get there and bring back. But there's another group of asteroids which are becoming increasingly understood and are closer to Earth. And these are called the near-Earth objects, and sometimes they're called near-Earth asteroids. So the acronyms would be NEO or NEA. These are going to be cheaper to reach and mine because they're much closer. So here we can see the two places that we have asteroids. One is in the asteroid belt between Mars and Jupiter, right? Earth is in there. And that doesn't seem like it's that far, but remember, it takes almost a year to get to Mars from Earth, so it's going to take even longer to get to the asteroid belt. And we can talk about the distance. So the Earth is, by definition, 1 AU, 1 astronomical unit from the sun. And the asteroid belt is on the order of 2 AU. Now, in contrast, near-Earth objects or asteroids are defined by having orbits around the sun that pass within 0.3 AU of the Earth. So we really didn't know anything about these up until recently. This is the cumulative number of discovered NEOs or NEAs. And you can see that, number one, the big ones we found first in red, but there aren't very many of those, you know, on the order of 1 kilometer or bigger. And then the ones that are, you know, not quite so big, but still pretty big, 140 meters across or bigger. You know, there's a lot more of them. And then these small ones, you know, less than 140 meters, we're really getting good at discovering them. So right now we've got about, there's actually, this was 2016. Right now we know about 40,000 of them. So, you know, picking out one to focus on is going to be part of the challenge. So we need an exploration phase to understand what the variety of these objects are, and then target the elements according to the sort of list that we've been talking about and what the economics are on Earth, and figure out which kinds of asteroids have those. So what do we know about the composition of these near-Earth objects? So we have evidence about them from studying meteorites and from reflectance spectroscopy and from a few return missions. So there's different kinds of meteorites, and that leads us to think there's different kinds of asteroids. We don't know where they are in many cases, but you know, there are things that are undifferentiated, where the body never got big and hot enough to melt, and so you get something that's very much like the original stuff the solar system was made out of. Those are the chondritic meteorites. And then we have the metal bodies, which represent the core, the iron nickel core of some kind of a differentiated body. And then there's things like pallasites, which are sort of a mixture of the core and the mantle, because those are big olivines stuck in metal. And then the achondritic stony meteorites, which are the crust. So these are the meteorites, and these are how we assign the asteroids to the different types. Asteroid type C for chondritic, asteroid type M for metal, asteroid type S for stony. So these undifferentiated meteorites, the chondrites, they're going to have lots of water and volatiles. They're going to be best for ISRU, in situ resource utilization. The differentiated meteorites, especially the irons, are going to be richer in platinum group elements. They're going to be better for high value mining that you bring back to Earth. So let's talk about meteorites. Meteorites, we basically know what's out there. We just don't know where it's out there, because we can see the things that fall on Earth. So there are two kinds of meteorites. There are fines and there are falls. Fines are where you're out walking around and you stumble on a rock and you go, oh, that's a meteorite. A fall is where you look up in the night sky and you see a streak in the sky, and then you go over to where the streak ended and you see a crater, and in the bottom of it is a big rock. So that's fall. So if we're just counting falls for the world and for North America, we see that the vast majority of them are stony meteorites, mostly chondrites, and the same thing is true North America, slight differences. So the irons are a relatively small proportion of the falls, although they're disproportionately represented among the finds and in the public's imagination, because whenever somebody shows a meteorite, it's always an iron meteorite with the beautiful Widmanstatten pattern, but those bodies are relatively rare if the number of meteorite falls is representative of the number of bodies out there. But we don't know that it is. Now, these things are classified in a number of ways. This isn't a class on meteorites. We just finished that, but we can see that we can differentiate the two, all meteorites into two great classes: the undifferentiated and the chondrites and those things, and then the differentiated. And some of those come from other planets, but that's a whole interesting field in its own right. But the point is, they're undifferentiated and differentiated meteorites, and they represent fundamentally different targets for asteroid mining. Just pop your hand up. I'll try and pay attention. That's sometimes hard. But someone will speak up and say, hey, I got a question. All right, so NASA has a relatively recent division that Congress required called Planetary Defense. And they are responsible for identifying, asteroid threats to the planet and coming up with strategies for ameliorating the problem. So they publish a monthly infographic about the near-Earth asteroids. The latest one reported 39,000 NEAs of all sizes. The ones greater than a kilometer, there's 873 known. The ones greater than 140, there's 11,000 known. So they think that right now we've discovered about 45% of the total population. Most of the ones we're missing are ones that are pretty small, but there's a lot of them out there. It's going to take us a while to figure out which ones to go after. So these are, just so you get an idea of what their orbits look like. There's the sun, there's the Mercury, Venus, Earth, Mars. So by the definition of a near-Earth asteroid is that it passes within 0.3 AU of Earth's orbit. That doesn't mean it doesn't go way out beyond Earth's orbit. And then they are also classified into these four groups: Amors, Apollos, Ottens, and Atiras, depending on, whether the asteroid body intersects Earth's orbit. That the Amors don't, neither does the Atiras. Or if it does, the Apollos do, and so do the Ottens. The difference between them is the Apollos are mostly inside the Earth's, or mostly outside the Earth's orbit. The Ottens are mostly inside. That's how they do it. All right. So meteorites give an idea of NEO materials, but how do we figure out what individual asteroids are made up of? After all, we're going to have to go after one at a time. And the answer to that is reflectance spectroscopy. You're going, oh, what's that? Well, the sun shines on an asteroid, and the reflected electromagnetic radiation, visible in near infrared, contains information about the body's surface. So telescopes on the Earth will target one asteroid and measure the reflected sunlight in the atmospheric window. So we can do that between 0.3 and 2.5 micron wavelength. Remember, visible light, our eyes can see are sensitive to something like 0.35 to 0.78 microns. That's visible. So anything with longer wavelength than 0.8 or so is in near infrared, and that most of this is near infrared. So this is the visible and near infrared spectrum, and we can compare these spectra that we get from near Earth objects or any asteroid with the spectra we can measure in the lab. So just to think about this, it shouldn't be that hard to tell metallic meteorites because metal reflects more sunlight than chondrites. Chondrites are black, very dark. The problem is that a large chondritic body will reflect the same amount of light as a small metallic body. And unless we have independent way of knowing the size of the body, we can't decide whether that albedo corresponds to a metal or a chondritic body. However, many meteorites and their parent bodies have specific absorption features at specific wavelengths where less light is reflected than impossible. And there are well-known absorbance features for olivine, pyroxenes, and water in the wavelength interval of interest. So, as we said, there's three main types of asteroids, three main compositional classes, and here we're looking at the reflectance spectra for two of them. So the C-type, the chondrite asteroids are most common. They consist of clay and silicate rocks, are dark in color, have a low albedo. The S-types are made up of silicate minerals and nickel iron. These are the order and according to chondrites. The M-types are metallic. There's also that. And so this is one of the ways we can tell which kind it is, because this one's got a clear absorption feature. This is corresponding to, I believe, pyroxene. And this one does not have a very good absorption feature, but those are the kind of spectra that we'll use in this effort. And there's an entire classification of these bodies. It's called the Bustemio classification based on the nature of the reflectance spectra. We're not going to spend any time on that. And then for return to Earth, the high value materials. And that, as we said, is platinum, palladium, rhodium, iridium, osmium, ruthenium. Lots of uses for these things: catalysts, electronics, green energy tech, some and metallic asteroids. It's not some, but the asteroids are going to have concentrations that, although I haven't really looked at it, directly what a Bushveld ore is and what an iron metal, a metal meteorite, how that compares, but we will see something. about that in a bit. All right. So the way to do this is, first of all, identify the asteroid target, using spectroscopy, or that's about the only way, as we discussed. Launch to orbit, deploy the solar sails, for power, establish communications, verify all systems, and get underway. Then track, intercept, and land on the asteroid, mine the asteroid, eject the return canister and send it back to Earth, and then recover it, have reentry, recovery, and sail. So let's review which elements we're likely to go after. So there's the lithophile, there's the siderophile, chalcophile, and the atmophile. So we're not, maybe there's atmophile elements in the for in situ utilization, but we're not going to send those back to Earth. There's the chalcophile elements. There really aren't significant sulfides in meteorites, economically significant. It's the siderophile elements, the ones that follow metallic iron into the core, that we're interested in, because Earth's core and its elemental inventory is inaccessible to us, but the cores of other bodies and their cargo of platinum group elements and gold are. Those are the ones we're going to go after. And we're not going to go after lithophile elements. So that's, remind you where the platinum group elements are, right there in the middle of the periodic table. Those are the siderophile elements of interest. And as we said, iron meteorites are from the core of an asteroid. These are the M types. They should have, and we know that those types of meteorites have high PGEs. There you're looking at a typical slice of a iron meteorite with a very well-developed Widmanstätten pattern, which is simply the exsolution of nickel-rich iron and nickel-poor iron. Taenite is the nickel-rich and kamacite is the nickel-poor. And this pattern formed as the solid core cooled further and these two phases exsolved, much like you see in perthite. That's another good example of exsolution in solid state. All right, so here we're looking at the enrichments that we see. Oops, sorry. So these are the platinum group elements: osmium, iridium, ruthenium, rhenium, platinum, palladium, gold. The abundances in the upper continental crust, notice this is in parts per billion, right? 10 to the minus 9. And the abundance in iron meteorites in parts per million, 10 to the minus 6. So anything in here is 1,000 times concentrated over anything in here. Now, chondrites also have significant PGEs, but not as great as you see in the iron meteorites. So it might be that it's worthwhile to mine them for that as well. So the iron meteorite relative to the upper continental crust enrichment for these elements ranges from a few hundred times to 1,000,000 times. Okay, so those are huge enrichment factors, and they're worth money. So here's the abundance in nature. Here's the market price. Everybody knows gold is up to $3,300 an ounce. Palladium and platinum are worth something. Ruthenium is worth more. Osmium is worth a lot more. That's, so that makes it extremely attractive as a exploitation target. So here's a partial business plan for a PGE return mission. So these are cubic volume that you could get, which would be, on the order of 2,700 cubic inches, about half the size of a suitcase in centimeters. The mass, these are very dense elements. And that is in troy ounces. And looking at the spot price, I forget which element this is for. I guess this would be for, looks like platinum. Obviously you can multiply that. So a half a suitcase worth of platinum would be worth $42 million. And the price of getting into space now is going down. So it's economically advantageous. Let's go back now for the the in situ resource utilization. And we talked about that. Let's talk about this a little bit more. So this brings us to an interesting thing I'm kind of working on about comets and meteors, right? We always think they're different, right? Comets take a very long time to traverse the night sky because they're so far away, whereas meteors, they're a flash, right? We see meteor showers. Comets are visible for weeks or months. Meteors are visible for seconds. We think these things are completely different. And then, that is the comet tail. And basically, it's sunlight reflecting off the dust that's coming off of the comet that's being ejected because the ice that the comet's is made of is slowly sublimating, basically breaking down due to heating. All right. Now, here is a near-Earth object that we recently visited and brought back some material from. This is called Bennu. That number corresponds to the number of asteroid that was discovered. So it was discovered recently, 245 diameters. This is a C-type, carbonaceous type. We knew that from its spectrum. When we brought back samples, we confirmed that. We call this a rubble pile asteroid. We don't understand. It's just a big pile of rubble. Nothing holds it together very well. Now, one of the questions that we have is, do comets evolve into rubble piles with multiple trips around the sun? So this is a comet 67P Churyumov-Gerasimenko. And what I think you can see there, here's a map of its surface, is rocks and ice, right? This is still a comet, so it's still spewing out material, but eventually the ice will be gone, and it may be that these near-Earth asteroids, rubble piles, are basically the remnants of dead comets. All right, so black dot on this shows where they found some CO2 ice, I guess down there. Water ice are indicated by red, green, and blue and yellow dots. So there's a lot of water ice and some CO2 ice on this body. All right, so how could that happen? So this is what I've been thinking about. So you start off with a comet coming from the Kuiper belt, way out beyond the orbit of Pluto. And it comes in, for whatever reason, something kicks it into a sun-crossing orbit. And it's a very elliptical orbit, just hugely elliptical. But what happens as it comes close to the sun, it heats up and it starts spewing, the ice starts melting, and that exerts a thrust away from the sun, very small. But with time, with multiple repetitions, that highly elliptical orbit will slowly become less elliptical. And it could be that eventually many of these comets evolve into orbits that are, which we would now classify as near-Earth asteroids. Okay, so what would that mean for what's happening on the inside? Well, what it means is, over here we have a comet, and we got a bunch of rocks embedded in ice. And, with every passage around the sun, more of this ice is going to burn away. That'll leave the rocks. And eventually you'll end up with, a thick, rocky thing like we see on Bennu, and then something in the interior where the ice is still preserved. Yes, Clint. Yes.
Just wondering, right, so the comet, the body containing water ice nearing the sun, so the melting and outgassing would be on the side facing the sun. And so it would be like
Yeah.
kind of like almost a thruster or
Yeah.
something. But the tail, and this is, you associate this tail, except that tail is not indicating thrust like a rocket. It's in fact the opposite. Right?
Well, you don't know where the tail is. When you see the body in the sky, when you see a comet in the sky, you see the comet and the dust tail. It doesn't show
Right.
you which side of the sun that it's coming from.
No, but I mean, there's only one side that's going to have melting going on.
Yes, sublimation, because melting implies it's
Right.
transition
Yeah.
to water.
Straight to gas. Anyway,
Yeah.
carry on.
No, it's well without outside of my comfort zone, but it's just hella interesting. Okay, so this is how I see it, from comet to carbonaceous chondrite rubble pile. This is the comet nucleus before the first trip around the sun. Lots of rocks embedded in ice. And then after more and more trips around the sun, the ice is only present in the middle. Maybe there's some bodies that have no ice whatsoever, and all we have are just the rocks. So how to mine volatiles from the core of rubble pile NEAs? Well, I think it's pretty easy. Just, make a borehole into its icy interior, heat the bottom of the hole to melt the ice, and then capture the fluids and gases as it comes out. Easy peasy. Now, there's a company called Astroforge, which is doing this. It mining asteroids, not going after rubble piles. They're focused on platinum group elements. They're not going after in situ utilization, right? The in situ utilization, there's a problem, right? There's nobody that's in the market for buying stuff to replenish things in space, but there's an expectation that market will appear. Which comes first, the resource or the market? I imagine the market first. But there's already a market for platinum group metals. So Astroforge is addressing that opportunity. This is a NEA mining company on a mission to extract valuable metals from asteroids, starting with platinum group metals. The company was founded in 2022, and they have had one space mission called Odin. It was built in 10 months for under $3.5 million and was launched in February this year. The mission was about more than just reaching a metallic asteroid. It was about proving that they could move fast, take calculated risk, build a complex spacecraft without a $1 billion price tag. They made it past the moon, got a few signals back, proved they could do and launch something, but they had communications issues. So they're putting a good face on what was in many ways a failure. But they're going to have another mission, which is scheduled for launch in mid to late 2026 on a SpaceX Falcon 9, and it's planned to land on the target NEA. So here's the company. I think their headquarters are in Seal Beach in Los Angeles. They have about 40 employees. And their business plan, it doesn't require that they, have a economic positive cash flow from returning platinum group metals to the earth. Like and this is what venture-backed tech companies will say it's about building the tools and proving them out so that whatever they're doing can be proved as a real capability. And then over time, as we get better and better at it and it gets cheaper, it will become economic. We see that over and over in the new fields like this. Astroforge
Did they
is
say how
mainly.
much?
Go ahead.
Did they say
What-
how much money they had raised and who they raised from?
Well, they raise it from investors.
Right, I meant like specific investors, because like there's smart money and then there's dumb money. And so sometimes knowing who invested can help understand the actual potential.
I do not have a list of their investors, nor would I expect them to share it with me. One of the things I was interested when I heard about this company was to know which asteroid are they looking at and why do they think it's metal. And I was told, don't worry about that. We're not going to tell you because think about the legal issues. If we share that with anybody, then they could go there too. Now, the legal issues aren't really settled yet. Now, let's imagine we do want to mine an asteroid. Who do we have to ask permission from? Or do we have to ask permission from? And what happens if another company says, oh, that's a good asteroid. I think we'll try and mine it too. Can you own? Do you have, I mean, in mining on Earth, you have a lease. There's some kind of a way of getting access to the property for the purposes of mining. That doesn't exist yet for asteroid mining. So this is another huge area of opportunity, perhaps. But what Astroforge is trying to do, I'm not sure that answered your question, but it certainly talked around it, if not at it.
There, I was just gonna, oh God.
Go ahead.
Sorry. I briefly did on space law. And one thing he taught me was that most of it is based on like kind of international waters law, with this idea that just once you're above like national airspace, it's all governed by those same laws. So is there a precedent for like mining in international waters?
Oh, well, I'll let Matt, that'll be the next lecture we have today. We've got I would have to say, a very interesting selection of lectures today. You know, first we'll get to that. So Astroforge, they say they're mainly in the business of building robust spacecraft that can go into deep space, find and zero in on an asteroid, land on it, and show that they can mine it. And the way they're going to mine it is they're going to ablate it, to vaporize the surface and then capture that vapor in the spacecraft. So they say that if they can bring back just 5 grams of commercially mined material, the firm would increase in value tremendously to becoming a $1 to $10 billion company, because then it's just a matter of scaling it up with cheaper access to space, and access to space, as I said, is getting cheaper and cheaper. They only need to find one asteroid with a decent platinum group metal concentration. And even if they do get into, if they do become a $1 to $10 billion company, they're going to have a lot more cash to grow that team. And they will be able to, once they get going, they'll be able to mine one for years or even decades. They just need one, to get to one. And we know that things are going to get cheaper and cheaper, right? And they're pretty sure that they will eventually find it. So this is the mission, Vestry. So Vestry aims to land on a targeted M-type iron asteroid, near-Earth asteroid, measure the abundance of platinum group metals, like platinum, palladium, for example. They're just going to go there and try and measure it. And the launch date isn't set yet, but it'll be sometime in late spring through the fall. That's what they're saying. So the spacecraft mass is about 200 kilograms. And that's what it's going to do. So stay tuned.